Welcome back to Applied Mathematics. In this video, I want to talk you through transformations of graphs. The basic idea here is that we're going to assume that we know what the graph of some function y equals f of x looks like. And we want to be able to use that information to turn that into the graph of something else that we can write in terms of f of x. And specifically, we're going to look at three ways we can change the function. We're going to multiply in front, a times f of x. We're going to add or subtract inside. Traditionally, this takes the form of x minus h, and then we're going to add or subtract outside. Generally, we write plus k here. Why do we use h and k? I have no idea. I have been told that it has something to do with the German words for horizontal and vertical, but I don't speak German, and I haven't been able to verify that. To understand what we're doing with all of these, let's jump over to a numerical graphing tool in Desmos. And let me get my head out of the way so we can look here, and you can see that I have in dotted blue a graph of an arbitrarily chosen function. In this case, it was x cubed minus 5x plus 2, but the function itself doesn't matter. And then I have on top of it exactly that expression that we've been introduced to, a times f of x minus h plus k. And then I have three sliders here that control a, h, and k. And so I just want to play with each of them in turn and see what happens. If I grab a, which is currently set to 1, I guess before I start into anything, you should notice what happens if you plug in a equals 1, h equals 0, and k equals 0. You'll get 1 times f of x minus 0 plus 0, which simplifies down to y equals f of x, exactly what we had graphed in the first place. So our graph of our equation and our graph of our function look identical to start. But if I grab that a equals 1 and I start to make it bigger, you'll see that the function kind of becomes taller. You can think of this as just grabbing the function and pulling it up and down. One of the things that I do want to point out here, though, is as you pull this function up and down like this, the zeros, the places where the graph crosses the x-axis, don't change. They stay in exactly the same place. Right? If I make a smaller than 1, we end up with a smaller function that's been kind of compressed. It's probably not going to be too much of a surprise to you. If I can hit it, there it goes. If I set a equal to 0, well, what happens if you plug in a equals 0? You have 0 times the function, and whatever that was, it comes out as 0. The interesting thing is, what if we keep going from there? And we switch and get the negative values. And I think if I go all the way to -1, it makes the most sense. At this point, the graph of our equation and the graph of our function are mirror images of each other. Our equation goes down when the function goes up. Our equation goes up when the function goes down. So putting a negative in front flips the graph upside down. And then we can still stretch and shrink from there. All right, let's go back to a equals 1 so that we don't have to worry about that anymore. And let's think about the other ones. I don't know if I mentioned it. We use a here. That often is used to stand for amplitude. How big is the function? So I hope that makes a little bit of sense. The variables h and k don't necessarily immediately make you think of horizontal and vertical. But now that you know that, it's probably not that much of a surprise that as I move h, the graph moves around horizontally. And if I change k, the graph moves around vertically. All right, so those are the basic ideas. Those are the three tools that we have. That's not the button I wanted to hit. That's the button I wanted to hit. It doesn't matter. We can go back there. We can go wherever I want to go. Those are the three tools that we have for dealing with the transformation of a graph. At this point, you're probably asking yourself, well, that's all well and good, but I'm just going to use my computer software and it's going to draw the graph and it will do whatever I tell it to do. Which is fantastic in an example like the one we just finished, where you have the equation of the function that you're graphing. The world doesn't always treat us that kindly. Very often, the functions that we're going to be dealing with in real-world situations are developed heuristically. Either it is a case of somebody collected some data and played a game of connect the dots, or somebody just drew out, I want the function to do this, and then I want the function to do that. So we have a graph, but we don't really have an equation that gives us the graph. Then, to make things more fun, translations are things that absolutely do happen all the time. My personal favorite application is in CNC machining, computer numerical controlled manufacture. If you have a computer controlled mill and you have a block that you're trying to mill out, a particular framework that you're trying to mill out, and you want not just one of them, but 2 or 3 or 4, you need to be able to figure out what the other pieces are doing given the first one. So you have to take the equation, the graphical representation of the function that describes the first figure, and translate it over to an empty space so that you can cut out a second one. Computers are very capable of doing that, but at some point, somebody has to teach the computer how to do it. And, well, one of the issues with CNC manufacturing right now is that there's not a whole lot of readily accessible off-the-shelf materials. Most of it is kind of cobbled together by hand in the back room of a shop. Certainly I have in my own basement a stack of CNC printers and mills that I've put together just out of spare parts that I was able to acquire over the years. There is no central place that I can go and get all of the materials that I need, all of the means that I need for manufacture, so I have to design a lot of the software for it on my own. And these sorts of skills absolutely come in handy for that sort of work. All right, so let's look at that next. Let's take a look at a function where the only thing we know that last bit didn't quite end up where I wanted it to. Let's fix that. That's close enough. All right, so we have a function that's doing this. One of the things that I want to very carefully point out here is that that part going through the origin is not a straight line. This line would continue like that. This line would continue like that. They are not straight lines. They are slightly bent from each other, but not by a whole lot. All right, but we have this kind of stretched out n looking figure. And this figure is the graph of y equals f of x. Our goal is to figure out how to graph y equals f of x minus 2. The graph here, if we go back to our prototype, right, a times f of x minus h plus k. Well, a in this case is 1, and we saw when a is 1, nothing really happens. K in this place is 0, and we saw when k is 0, nothing really happens. H is 2. And we saw that h caused the graph to shift horizontally to the left and to the right. I also want to point out that in the prototype we had a minus here, and we also have a minus here. So that is not negative 2. H is equal to 2. And with just that information, we can in fact figure out what this graph is going to end up looking like. So we had a point at negative 6, 0. It's going to shift over by 2. It's going to be 2 further to the right than it was before. So we were at negative 6. We move over 2 places, and that takes us to negative 4. All right, so that first point is now at negative 4, 0. The second point was at negative 3, 4. It's going to move over 2 places and suddenly be at negative 1, 4 instead. Likewise, our point from 0, 0 has now moved to the point 2, 0, 4, 3, is now at 6, negative 3, and 7, 0 is now at 9, 0. And with that, we have figured out what this graph is going to turn into. And we can play our game of connect the dots from there. For the sake of simplicity, I'm going to keep playing with this same original function because I have the ability to copy and paste, and you have the ability to just keep looking back to the same place on your page that you were before. But again, one of the big keys here is we could do this with any function we'd like. There's nothing special about this function. It just is a function, and that's all that matters. All right, let's say we want to shift a different way. Y equals f of x minus 2. Notice how similar this equation is from the previous one. We took the minus 2 that was inside the parentheses, and we moved it to the outside of the parentheses. That means we're going to switch from shifting horizontally to now shifting vertically. And if we scroll all the way back up to our prototype, what I want you to notice is that that negative is not built into the prototype. In the prototype, it was plus k. So k in this case is negative 2. We're going to shift downward. All right, I'm going to do my best to get the horizontal axis lined up here so that you can really see what's happening. But the basic idea is the same as before. We were at negative 6, 0. We move down by 2, and we are now at -6, -2. We were at -3, 4. We move down by 2. We're now at -3, 2. Likewise, our point from 0, 0 is going to move to 0, -2. Our point from 4, -3 is now going to be at 4, -5. And our point that was at 7, 0 is now at 7, -2. Play our game of connect the dots again, and we have this graph figured out. All right, one more time. How about this time we look at the graph of y equals 1/2 f of x. Well, this is a little bit different, right? We're not going to be shifting things around. When we had that power in front, it was going to stretch or shrink the graph vertically. And in this case, it is going to shrink because our a is 1/2, which is smaller than 1. One of the nice things we saw when we were looking at the graph in Desmos, the computer-generated version, is that points on the x-axis did not move. So we had -6, 0, we're still going to have -6, 0. We had 0, 0, we're still going to have 0, 0. We had 7, 0, we're still going to have 7, 0. It's the points that are away from the x-axis that are going to change. And mathematically, what we're going to do is multiply the y-coordinate. So our point -3, 4. The x-coordinate stays the same, and then we multiply our a times the y-coordinate to get the point -3, 2. Our point 4, -3, the x-coordinate stays the same. We multiply the y-coordinate by by 1/2, and we're going to, in this case, end up with 4. I think I'll write it as a decimal, -1.5. I am treating these as exact values, but decimal approximations are a lot easier to graph for most people. But 1.5 is right about there, halfway between 1 and 2. And then when I sketch this out, I still get that kind of N-looking shape, but now it's a much more stretched out looking N, or maybe it's a squashed looking N, whichever way you want to think about it. All right, one more and then we'll wrap up with this. What if I wanted to do several things all at once? Let's say that I want to graph y equals 2 times f of x plus 1 minus 3. Well, just going through and comparing to our prototype here, a is going to be 2, h is going to be negative 1, and k is going to be negative 3. One of the things that I find useful in dealing with several transformations at the same time is to create a table of points. We created tables of points in order to graph functions at the first place. So nothing new going on there. Right? The points we've been dealing with all lesson, negative 6, 0, negative 3, 4, 0, 0, 4, negative 3, and 7, 0. Right. And then I'll just apply my transformations in steps. How do I decide which one to apply first? The answer there is honestly too obvious, and that's what makes it so confusing. We'll follow the order of operations. Looking at our equation over here, we have multiplication, 2 multiplied times something, and then we have addition and subtraction. In the order of operations, multiplication happens first, so that's the first step I'm going to apply. So my x is going to stay the same, and then I'm going to have 2 times f of x as my other column. All right, so all of my x's stay the same. All of my y values get multiplied by 2. The points that were 0 stay 0. The points that weren't get doubled. All right. Then I apply my shifting, my addition and subtraction. Some people like to break this up further. If it makes it easier for you to do one shift first and the other shift in a second step, go for it. But I find that writing it out all in one go is easier on me, so that's what I'm going to do. Right. So this will take us to the thing we're actually trying to graph. And all I have to do is apply my shifting. The horizontal shift moves things in the negative direction by 1. So that's going to take all of the x coordinates and subtract 1 from them. Negative 6 becomes negative 7. Negative 3 becomes negative 4. 0 becomes negative 1. 4 becomes 3, and 7 becomes 6. My vertical shift is going to move things down by 3. That's going to subtract 3 from the y coordinates. So 0 minus 3 is negative 3. 8 minus 3 is 5. 0 minus 3 is still negative 3. Negative 6 minus 3 is negative 9. And 0 minus 3 is still negative 3. All right. With that, I have what I need. I'm going to copy this table so that I can put it on a clean sheet and continue working. The paper you're working with probably gives you plenty of space to keep working down the page, so you don't need to rewrite that table. But here we have it, just for our reference. I'll sketch out a new set of coordinate axes. And we're going to be going pretty low, so I'm going to put my x-axis relatively high. And then let's just start plotting points. And then once again, our game of connect the dots. And we have basically the same crooked looking letter N that we had before, only slightly sharper. It kind of looks slightly narrower to my eye, but that's an optical illusion. It is really just taller. It is exactly as wide as it was in the first place. All right, so that's the basic idea of transformations of graphs. You certainly can apply these techniques to graphs given to you algebraically. You can apply them by graphs given by tables or functions that are given by graph. It all works out. It all gives you the same sort of a result. This is the case that I find is the most interesting. It's the place where technology has not allowed us to get away from doing things by hand the way they've been doing since the 1800s. I think that's more than enough to get through one video, so I'll wrap up here. As always, thank you for joining me. I'll see you next time.